And I'm going to share my screen, and I'm going to open the chat, and I'm going to go into my math lab. And in my math lab, I'm going to go to the assignment manager. And in the assignment manager, I'm going to start by opening that quiz. And as we go over the quiz, for the quiz that you took personally, the quiz was written in such a way that the questions were in a different order for everybody, so they might not be the same order that you have. And they're the same questions, just the numbers might have changed from version to version. So it might not be identical to the problems that you had, but it will be similar. You submitted work for me in Blackboard. I do believe that you should be able to go back and look in Blackboard. I graded your virtual work on the tablet with my virtual pen, and I think through the Blackboard gradebook, you should be able to click on it and open up and see the graded paper with my annotations on it. After class, if somebody could go through and look and see if that is indeed the case and let me know. If it isn't, I will try to do it another way, but hopefully it works. So let's start with this first problem. I think this first problem was probably the most problematic for most people in class. Order of operations, be very careful. And also the other thing that I think got some people is penmanship, of all things. That numerator is 33 divided by 3 times 2 times the absolute value of 2 squared plus 3 squared, close the absolute value bars, over 6 plus 4 minus 6 squared. First of all, there were some people who, when they wrote this problem down, the first time they wrote it with a division symbol, and then as they went from line to line to line, that division symbol morphed into an addition sign. Be careful, watch your penmanship. Second, when you approach a problem like this, you should use your order of operations, and you need to remember there's an invisible parentheses around the numerator and likewise around the denominator. So I'm going to go through and simplify the numerator first and then simplify the denominator. In the numerator, work inside. Inside brackets, well, rather than brackets, I have these absolute value symbols. Inside there, I have exponents, so I'll do that first. So this becomes 33 divided by 3 times 2 times the absolute value of, that becomes 4 plus 9. Be careful, that's 3 to the second, not 3 times 2. There were a handful of people who put 6 instead of 9. Then working inside, 4 plus 9 is 13, and the absolute value of 13 is 13. So that becomes 33 divided by 3 times 2 times positive 13. Then order of operations. Do you remember we said it was PEMDAS? And the multiplication and division is all one step as they come from left to right. So in simplifying this, you really need to divide by that 33 by 3 before you multiply. So that becomes 11 times 2 times 13. So 22 times 13 is, oh Lord, I'm hitting a blank.
286.
286, thank you. So a couple places, division stays division, watch it when you square, simplify inside. The only time you'd need to distribute is if there were a variable on the inside. Otherwise, it's all numbers, you should be able to simplify. Watch squaring. Now in the denominator, 6 plus 4 minus 6 to the second, exponents first. So that becomes 6 plus 4 minus 36. And addition and subtraction as they come from left to right. So that becomes 10 minus 36, which becomes a negative 26. And so over here, when I divide by that negative, I should get a negative number, and it should turn out to be negative 11. That one any better? I know some people, when you look at something that involved, it becomes overwhelming. Part of the reasons we have for that order of operations is that we don't do it all at once. We do it in small steps at a time. That one okay for everybody?
Yes.
Okay. Then next, here we've got absolute value. We're taking the absolute value of x minus y. We're told to substitute in 7 for x, minus negative 8 for y. And again, inside those bars, simplify first. 7 minus negative 8 is 15, and the absolute value of 15 would just be 15. I think that one was all right for most people. Next one, write the English phrase as an algebraic expression, simplify. They tell us to let x represent the number. I think there was somebody who used a letter other than x. If they tell you what variable to use, you probably ought to use it. It says we're taking the difference, so that means I'm subtracting between the product of 6 and the number. Product means multiply, so that would be 6 times my number, and 2 times the number would be 2x. That's the expression. And then when I simplify, 6x minus 2x is 4x. How's that one? Can I clear it?
Good.
Good, thank you. Next one, this one was a little bit more involved. A few more people had problems with this. We have 2 minus 7 brackets 5 minus parentheses 2y minus 6. In addition to penmanship errors, there were a few people that somewhere in the middle of a problem changed operations. After you distribute, you can't just turn addition or subtraction into multiplication. So be careful with what's written. What do I mean by that? Order of operations, we start inside. I cannot combine those. So I have to distribute to get them out of parentheses. There's no number in front, so I'm going to put a 1. So inside the brackets, that's going to be 5. Then when I take negative 1 times 2y, I get minus 2y. That's subtraction. It's not multiplication. There was never multiplication between the 5 and the parentheses, so you can't turn it into multiplication. Then I'm going to take the negative 1 times the minus 6 to get plus 6. And so inside there, I have negative 2y plus 11. Now I've got 2 minus 7 times that. Order of operations, you have to remember that you have to multiply before you subtract. There were an awful lot of people who did the subtraction first. You cannot subtract until after we multiply. So now what we have to do is distribute that negative 7. Gives me 2y. Negative times negative is positive 14y. Negative times positive is negative 77. And then combining like terms, I get 14y minus 75. How's that one?
Good, thank you.
And then next, simplify the algebraic expression, more of the same. We have 4 parentheses, 3x plus 5, close parentheses, minus 12. We cannot do anything inside, so to get it out of parentheses, we have to distribute the 4. Here we're going to multiply by the 4 because since there's no symbol in between, I'm multiplying. gives me 12x plus 20 minus 12. And then like terms, 20 minus 12 is positive 8. Kind of the same, as similar to the first one, just not quite as involved. Is everybody all right with this one?
Yep.
Yeah.
Okay, great. Then next, this one, it says to rewrite the expression without absolute value bars. So let's see, that negative 12 is just negative 12. In the denominator, the absolute value of negative 12 is 12. Some people stopped there, but over here the directions say simplify your answer. And if I were to take negative 12 and divide it by 12, I should get negative 1. That one okay?
Yeah.
Yep.
And then lastly, we need to evaluate this expression. So we've got 7 plus 7 times x minus 3, but we're told to put in 6 for x. So 6 minus 3 quantity cubed. Be careful with this. Order of operations says to start inside. They're just numbers, so I'm going to start by doing that subtraction. 6 minus 3 is 3. Then after the parentheses, I'm going to do exponents. 3 to the third is 3 times 3 times 3, gives me 27. Then I'm going to multiply. 7 times 27 is 49, and 140, 189. And so when I add, my final answer is 196. How's that one?
Why wouldn't you distribute the exponent to 6? Like turning it into 216 minus 27?
Because there's subtraction in there. When we were going over our exponent rules, if I had a product, I just raised each factor to the power. But this is not multiplication. And so over addition and subtraction, I can't just raise each term to a power. Plus, you're supposed to do inside parentheses first. And I think it's easier to subtract 6 minus 3 and then just take that 3 to the third. If you can simplify what's inside the parentheses, you've got to do that first. All right? Anything else? If not, that was the quiz. Next thing I think I promised I would do is I said that I would look at homework questions if anybody had questions on the questions. So the homework that's due today, that P2, exponents in scientific notation, there were a couple in there that got a little involved. You know, some people emailed me questions and I tried to type back answers. Hopefully they were clear enough. Before I go over ones that people asked me about, does anybody have questions on their own from any of the homework problems? Does anybody want to look at any of the problems from this assignment?
I was wondering if you could go over question 28 on P3.
On P3, before we go to P3, let's look at P2, okay? Does anybody have a question on any of the ones from homework P2? If I were to open the grade book right now, everybody's done them all and they have 100 on them and nobody's wondering about any of them?
This is the homework due for tonight, correct?
Yes.
Yeah, I didn't start it yet.
Okay. All right, those of you who started it, are there any questions? Should I just intrinsically go over the 3 that I got a lot of email on or no?
I just
Yeah.
have a question for when you get to homework, the section P3 one.
Okay. Well, at the end of P3, that's, we're going to start looking at that stuff today. So it might just be that it was something that we hadn't covered in class yet, but we'll look at it.
Yeah, I was at
Um,
number 5, I think, or 6.
Okay. So this one deals with exponents. Order of operations, we look inside the parentheses, but there's really no work to be done in there. It's all multiplication. So then next we do exponents. And over here, that's just multiplication that I'm raising to a power. And if it's multiplication, everything gets raised to that power. Now, when I multiply on the same base, I add exponents. 1 plus -4 is -3. -5 plus -4 gives me x to the -9. The y and the z get left alone. And then when it says use positive exponents only, any factor that has a negative exponent will be rewritten with a positive exponent when it moves to the denominator of the fraction. Anything with a positive exponent is going to go in the numerator. And then with this one, we're not quite done. We have to replace the 2 to the 3rd with 8. How's that one? Okay, no questions. Does anybody want to look at this one, or are you guys all good?
All good.
All good? All right, then I guess we'll just leave and go to homework P3.
Someone asked you to look at it.
Okay. Then we got to go back. Sorry about that. That was 35. With this one, what we have inside the parentheses is x to the 6, y to the 4th, z to the 2nd, over x to the -6, y to the -4, z to the -2, and all of that's being raised to a power. The order of operations tells me to start inside. In the parentheses, I can divide. When I divide, I subtract exponents. 6 minus -6 is positive 12. 4 minus -4 is positive 8. 2 minus -2 is positive 4. Now we'll raise that to the power. Because it's all multiplication, I'll raise each factor to a power. When I raise a power to a power, I multiply exponents, giving me x to the -12. I'm sorry, I take that back. 12 times 3 is not negative. 12 times 3 is not -12. I'm sorry. 12 times 3 is -36. 8 times -3 is -24. 4 times -3 is -12. And now to write it without negative exponents, any factor with a negative exponent, that exponent becomes
Shouldn't that be a
positive.
Z?
What?
Shouldn't that be a Z at the end?
Yes, it should. Thank you. I'm sorry, my phone was ringing. I hit it.
No, it's okay.
And so that gives me z to the 12. And then if there's nothing left in the numerator, we'll put that 1. Better?
Yes.
Okay. Should we go on to P3 now?
Yeah.
And when it says freeze, I don't want to see anybody moving. I want to see everyone frozen.
Okay. I'm sorry, it takes me a while. Which question in homework P3 were you wondering about?
think 5 or 6.
5 or 6? Okay.
Yeah. I think it was like in a square root and it said 75.
Okay, that's actually where we're going to be starting today, is looking at that idea of simplifying radicals. Let me look at it. Yep, you might have hit 75 instead of 45. Can I leave this problem open and can I go back to it as an example when we get to that point in today's notes?
Yep. Thank you.
Great. Then, let's see. Let me just make sure that we are recording. Yeah, we are. And then let me go back to screen share. And let's go to today's notes. And today, what we're going to be looking at, today is September 14th. And we're going to look more at radicals and rational exponents. And so last class, we talked about the idea of a square root. We talked about the idea of notation, whether there was a plus or minus there. So for example, we said that if I asked for the square root of 100, written that way, it would be 10. If I asked for the negative square root of 100, it would be negative 10. But every number has 2 roots, and if I wanted both the positive and the negative, I would have that plus minus sign, and I would put both answers 10 or negative 10. Everybody comfortable there?
Yep.
Then we also, I believe, said that if I took the square root of x squared, that turns out to equal the absolute value of x. I believe that was where we finished. Look at an example. If I took something like the square root of negative 7 squared, that would give me order of operations. I'd start inside. Negative 7 squared is positive 49. And because we're looking at the principal root, there's no minus sign in front. That's 7. And so when I look for the square root of a number squared, I end up getting its square root. What we did not look at last class is what happens if that radicand is negative. For example, if I took the square root of negative 81, what would I get? By definition, we're looking for something that when we square it, we get negative 81.
Isn't that not possible?
It's not possible. Does not work. And so we're going to say that if the radicand is negative, there is no real square root. So it's not real, and there's no square root. We're going to find, hopefully before the end of today, that there are roots, just not square roots or second roots. So far so good.
Yep.
If so, we're going to start looking then at rules for radicals. And if anybody's familiar, I am not referring to the book by Solomonsky about protesting and things like that, but rather I'm looking for operations on radical expressions. And we're going to have a couple. We're going to have a product rule. And the product rule says if I have the square root of A times the square root of B, as long as the radicals are the same, That's going to give me the square root of A times B. And we're going to find that equality is a two-way street. And so sometimes we're going to say that the square root of A times B is equal to the square root of A times the square root of B. Same rule, just working backwards. Likewise, we're going to have a quotient rule. That says the square, I apologize. That says the square root of A divided by B is equal to the square root of A divided by the square root of B. Or sometimes if I have the square root of A divided by the square root of B, I'm going to think of that as the square root of A over B. Again, those are qualities of two-way streets. It can work both directions. We're going to use those rules when we multiply and divide. So let's look at first some examples that make use of that. If I have the square root of 3 times the square root of 27, well, that's the square root of 3 times 27. And what does 3 times 27 give me?
81.
81. And can we take the root of 81? Sure, the square root of 81 is 9. Likewise, if I have the square root of 32 times the square root of 2, well, when I take 32 times 2, what do I get?
64,
And can I take the root of 64?
8.
8. Okay, just a second, folks. Amy called. Do you want to call her back? She texted me. She's raging. I don't know what's going on. Sorry about that. Next example, if I have the square root of 20 divided by the square root of 5, because they're both square roots, I can think of that as the square root of 20 divided by 5. 20 divided by 5 is
4,
4, and the square root of 4 is
2.
And then if I have the square root one more, the square root of 162 divided by the square root of 2, that would be the square root of 162 divided by 2, which gives me the square root of 81, which is 9. And so sometimes we're going to find that with products and quotients, it's going to be easier to simplify them if we first multiply before we take the root, or if we first divide before we take the root. There are other times, though, when we want to work backwards. And when we want to work backwards, it's when we focus on the idea of putting a radical in simplest form. And I know sometimes students look at the simplest form and say, that doesn't look simpler, it looks more complicated. We're going to find that there are times when we can do operations once it's in simplest form that we can't do otherwise. And also way back in the pre-calculator days, putting a radical in simplest form actually did make the computation simpler. We're going to say a radical is in simplest form if, and we're going to have 3 criteria. First criteria is that the radicand has no perfect, and for now we're just going to talk about perfect squares, but we'll find later that it could be other powers, factors. We're going to say that a radical is in simplest form if the radicand is not a fraction. And we're going to say that a rational expression, so a fraction, can have no radical in the denominator. So an irrational expression has no radical in the denominator. And so those are the things we're going to be looking at. Getting radical factors out of the perfect square factors out of the radical, making sure that we don't have a fraction under the square root, and making sure that we don't have a square root in the denominator. Everybody all right, or do I need to wait a minute? Hearing nothing, I'm going to turn the page. When I look at this simplifying radicals, I find it easier if I have a list of perfect squares on the side. And so for that list of perfect squares, if I take 1 and square it, 1 squared is 1. So 1 is a perfect square, 2 squared is 4. So 4 is a perfect square. 3 squared is, anybody?
9,
9. 4 squared is,
16,
16,
5 squared is,
25,
25,
6 squared is,
36,
7 squared is,
49,
8 squared,
64,
9 squared,
81,
10 squared,
100,
11,
121,
12,
64.
144,
Oh yeah, 144. Lol.
144. And usually I try to go higher, but usually I'm working on a document camera and not a Surface. I think we can fit one more in here. Anybody know 13 squared? 169. So to simplify a radical, and we don't want it to have any perfect square factors in the numerator. So I'm going to start with a pretty simple example. I'm going to look at the square root of 18. What we want to do is we want to find the largest perfect square factor of the radicand. So, which of those perfect squares goes into 18 evenly?
9 times 2.
9 times 2. Then we're going to use our product rule. So the square root of 9 times 2 is the square root of 9 times the square root of 2. And then we're going to simplify. The square root of 9 is 3 radical 2. And so this 3 radical 2 is considered simplest form. Is this a process you folks might have seen before?
yes,
Some yeses, any no's? We do a few more. If I look at the square root of 75, which number that's a perfect square goes into 75 evenly?
is it 5 square roots of 3?
Well, it's going to eventually be 5 square roots of 3. I want to show the in-between steps to start. 75 is 25 times 3. I'm going to give them each their own radical. Square root of 25 times the square root of 3 gives me 5 square roots of 3. Now, I think that one that we pulled up on My Math Lab asks us to simplify the square root of 45. Oh, sorry about that. If I look at the square root of 45, which of those perfect square factors goes into 45 evenly? What numbers multiply to 45?
9 times 5.
9 times 5. So we'll take the square root of 9 times the square root of 5. And so simplest form, that would be 3 square roots of 5. That one all right. Next one, I want to look at a couple of ways. If I say the square root of 32, what numbers can you folks think of that multiply to 32, where one of the numbers is a perfect square?
16 times
4.
2.
Okay, I heard two answers. Let's do the 16 times 2 first. So that gives me the square root of 16 times the square root of 2, which would give me 4 radical 2. The other answer that I heard was fine. We could look at that as 4 times 8. We'll take the square root of 4 times the square root of 8, which would give me 2 radical 8. But we're not done yet now, because 8 still has a perfect square factor. We can take that further, because 8 is 4 times 2. So that gives me 2 times the square root of 2. And it takes me to 4 radical 2. So thank you. I wanted to hear both possibilities. Thanks for both volunteers. Do you see, eventually they take me to the same place. But if we use the larger number, it turns out to be a heck of a lot less work. I'm going to turn the page and start adding some variables to this mix. What if I have the square root of 81x to the 4th? I can think of that as the square root of 81 times the square root of x to the 4th. And now to find the square root of x to the 4th, I'm wondering, what can I square to get x to the 4th? What would go in here? What can I multiply by itself to get x to the 4th?
X squared.
Yeah, wouldn't it be x squared? Because when I raise a power to a power, I multiply those exponents. And so to take the root of a variable with an even exponent, we have the exponent. So here the square root of 81 is 9. The square root of x to the 4th is x to the 2nd. And I apologize, I didn't mean take the root, I meant take the square root. Again, we're going to find other roots later. And with this one, that's fine, because over here, is everybody all right? No matter what x is, x squared is positive. Instead, if I looked to take the square root of x to the 6th, well, half of 6 is 3. But, and you're going to find sometimes my math lab makes you put it in, and sometimes they're not that picky and they don't. But you know how way back at the beginning we said the square root is like the absolute value. If I have an odd exponent, there's a chance that that could be a negative number. So I need to throw that in absolute value box. That's all right. Let's look at a few more. Let's say I want to simplify the square root of 300x to the 12th. What perfect square goes into 300 evenly?
100 times 3.
That's 100 times 3, and that x to the 12th has an even exponent, so I can take its root. Now, not everybody likes to do it, but I think it avoids careless mistakes if we take the time to rewrite that, giving each factor its own radical. Then the square root of 100 is 10. I cannot take the square root of 3, so that stays inside. And the square root of x to the 10th is x to the 6th. Technically, you could probably stop there, but it's most normal to take those factors that are out of the radical and write it in front. So we're going to write this as 10x to the 6th times the square root of 3. I'd like to put everything that's not in the radical if it's multiplying out in front, because I know sometimes I have a tendency to be a messy writer, and all of a sudden you look at something like that and you say, hey, is that x inside or outside? And by moving things that are outside in front, you avoid that ambiguity. So far, so good? So then, what happens if I have something like the square root of x to the 9th? Because that's an odd exponent, it's not a perfect square. And so if I'm trying to simplify the square root of an odd exponent, we're going to take one factor out. Not out of the radical, but out of the exponential expression. What I mean by that is that x to the 9th. Can I think of that as x to the 8th times x to the 1st? It equals the same thing.
Yep.
But now I've got an even exponent and the smallest possible odd exponent. So I'm going to take the square root of the x to the 8th times the square root of x, and that's going to give me x to the 4th times the square root of x. And believe it or not, this is considered simplifying. That's the simplest form. That one all right? So let's
Yeah.
look.
Yeah.
If you guys are doing all right with this, let's just look at one more of these. Let's look at the square root of 243 x to the 2nd y to the 5th. And I'm going to shut up and have you folks work on this one for a minute. Did anybody come up with two numbers? One a perfect square that goes into 243 evenly. Any ideas?
81 and 3.
So that becomes 81 times 3, beautiful. X squared stays because it's even. And what should we do with that y to the 5th?
Y to the 4th
Make
times y.
and
Beautiful. Then we'll take the square root of 81, the square root of 3, the square root of x squared, the square root of y to the 4th, and the square root of y. Perfect squares, the square root of 81 is 9. The square root of x to the second. 2 divided by 2 is 1, x to the first. The square root of y to the fourth. 4 divided by 2 is 2. Hello, sorry about that. So those are my perfect squares. And then the others have to stay underneath the radical. That one all right? Everybody comfortable with this simplifying process? Does anybody want more, or are we good?
All right.
All right. If we're all right, then the next place that we're going to do is we're going to look at the idea of adding and subtracting radical expressions. And we're going to find that you can only combine like radicals. Just like we could only combine like terms, we can only combine like radicals. And like radicals need a couple of things to be the same. They have to have the same radicand, which means they have the same number underneath, or quantity expression underneath the square root symbol. And we're looking for the same root. And the root is given by something called the index. And right now, we're only going to be looking at square roots. We'll be looking at different indices later. We're going to combine like radicals. By adding their coefficients. And keeping the radical part the same. So again, that idea that addition and subtraction, they have to be the same in order to add and subtract them, and they stay the same. So what the heck does all of that mean? Is everybody caught up, or do you want me to wait a minute?
Wait 1 second.
Okay.
Yeah.
Let me know when you're done. You ready?
Yeah, you can go.
Okay. If I have 7 radical 5 plus 9 radical 5, you see how these two are the same. And so again, it's an application of distributive property. I'll add those coefficients, 7 plus 9, and the radical part remains the same. So I get 16 radical 5. They're like radicals, so I can add them. It's very similar to combining like terms. Another example, if I have 10 square roots of 7x minus 6 square roots of 7x, I'm going to look at those radicals. Are they the same?
Yeah.
Yep, so we'll just subtract this time the coefficients to get 4 radical 7x. And one more before we turn the page. What if I have 2 radical 3 plus radical 2 plus 5 radical 3? Do I have any like here?
Yeah, the 3.
The radical 3s are. And so those two I can add. 2 plus 5 will give me 7. It'll stay radical 3. And then that last one that's different, we're gonna just have to add it at the end. So 7 radical 3 plus radical 2. That one okay?
Yep.
All right, then let's look at some that are a little bit more involved. Let's look at the square root of 75 plus the square root of 48. Is it obvious that those two are not like?
Yeah.
Yeah, but don't walk away from the problem and say it can't be done yet. Because what we have to do is we have to simplify first. That would be too easy if we could just say they're not like. So let's look at the square root of 75. How does that simplify? What number goes into 75 evenly that is a perfect square?
25.
25. So that's 25 times 3. So the square root of 25 is 5 times the square root of 3. Now, anybody offhand, can you think of the biggest perfect square that goes into 48 evenly?
16 times 3.
16 times 3. Now, is there anybody else who 16 times 3 was not the first thing that popped into your mind? Can I give you sort of a cheater's way of trying to get at that? Going in backwards. Over here, because I had a 3 left in the radical, what I'm going to do first is I'm going to take 48 and divide it by 3 and keep my fingers and toes crossed. Hopefully that'll give me a perfect square and I can add them. If it doesn't, they weren't meant to be added anyways. Make sense? So then the square root of 16 is 4 times the square root of 3. And now they're like, so I can add them and I get 9 times the square root of 3. And I'm done.
So if 48 divided by 3 didn't give, like, say it was a number that didn't give you a perfect square with 3, would you leave it at 75 plus 48?
No, they'd still want it in simplest form. But usually with these, if you're looking at 48 and you can't see a possibility, try dividing it by the 3 first. 9 times out of 10, it'll work. All right?
Yep, thank you.
So let's look at 3 times the square root of 8 minus the square root of 32 plus 3 times the square root of 72 minus the square root of 45. And right now, none of them are alike, but I think we can simplify all of them. Anybody have an idea as to what we should do with that 8? How should we factor it?
4.
4 times 2. That gives me 3 times the square root of 4 is 2 times the square root of 2, or 6 square roots of 2. So now what do you folks want to do with that 32?
-4 and 8.
We could do 4 and 8, but is there something bigger than 4 that goes in there? Does 2 go in there?
Yeah.
How many times?
16.
16. And you see by trying that 2 first, it gave me that largest square. So that'll give me the square root of 16 is 4 times the square root of 2. Again, you could do 4 and 8, but then you'd have to reduce twice because 8 can still be broken down. So then what's the largest square that goes into 72? invent my cheater's way. Does 2 go into 72?
36.
Yeah, and 36 is a perfect square. So do you see how that approach sometimes takes you to that largest factor? And so that gives me 3 times 6 times the square root of 2, or 18 radical 2. Now 45, 2 does not go into it. Oh, sad, sad day. But is there a perfect square that does go into 45?
9 and 5.
9 and 5. And the square root of 9 is 3. Now they're all simplified. I can combine the first 3. Again, they're all radical 2, so it'll stay radical 2. 6 minus 4 is 2, plus 18 is 20. And then that one that's not like just has to stay alongside. I also know there's some students that really don't like answers that look like that, and they pull out their calculator and change it to a decimal. When you pull out your calculator and change it to a decimal, what happens is you get an approximation, and so leaving it in radical form gives us that exact answer. And so this would be in simplest form. It would also be my exact answer. Anything that we do changing it into a decimal would involve rounding off. Enough of these. If so, next place that we're going to go is we're going to look at rational expressions containing radicals. And we have to rationalize the denominator. Which means that the denominator has to be a rational number, or it means that we want no radical left in the denominator. And also no fraction under the radical. So first of all, let's look at rationalizing the denominator. Well, actually, I'm tweaking this example. And let's look at having a fraction underneath the radical. If I have the square root of 1/2, everybody all right? We said no fractions underneath there. So we'll change that into the square root of 1 over the square root of 2, which gives me 1 over the square root of 2. So no fraction under radical. But we're not done yet because we want no radical in the denominator. And so what we're going to do is we're going to multiply both the numerator and the denominator of the fraction by the radical in the denominator. Or a radical that makes the denominator the perfect square. So worst case scenario, if you don't see anything else, you can multiply numerator and denominator each time by the radical in the denominator. Sometimes though, there's a smaller number you can use. It just makes you, it gives you less arithmetic to do, less computation to do. But if all else fails, you're going to multiply it by that radical that's in the denominator. So what the heck does that mean? Does everybody see this denominator contains the square root of 2? So I'm going to multiply both numerator and denominator by the square root of 2. I always write that out first because I want to make sure that I'm multiplying the numerator and denominator by the same thing. Because you see, what I'm really just multiplying it by is 1. It's when the numerator and denominator are the same, it's 1. So that gives me radical 2 over radical 2 times radical 2 would give me radical 4. And so now I'm going to simplify the denominator. And so that gives me radical 2 over 2. And so that would be my simplest form. And again, going back to ancient times, when I was a kid, to divide 1 by something, usually something that's like the square root of 2 is like you'd round to a 4 or 5 place decimal. Doing the division this way, you'd have this really long divisor, as opposed to doing the division this way, you're dividing by 2. And so it makes your arithmetic easier. Next example. If I have the square root of 2/3, first problem that arises is I have a fraction underneath. Before I do anything, can I reduce that fraction 2/3? I don't think so. So now I'm going to change that into the square root of 2 over the square root of 3. We're worried about the radical in the denominator. Numerator, I'm not going to worry about. Denominator, it's radical 3. So I'm going to multiply both numerator and denominator by radical 3. Again, I'm doing a little bit of a check here. Since I'm multiplying top and bottom by the same thing, I'm multiplying by 1, which means I'm not changing what it equals, just what it looks like. So that gives me radical 6 over radical 3 times radical 3 is radical 9, or radical 6 over 3. And I'm going to stop there. I'm done. Because the 3 is outside a radical and the 6 is inside a radical, I cannot do anything more with that fraction. I'm going to stop there.
If it gets to a point where it's like the numerator is able to be simplified, do we do that and just do nothing to the denominator?
Right.
Okay.
Unless if you multiply by too large a quantity, then sometimes you can simplify that denominator too. So what do I mean by that? Let's look at an example. Let's look at 2 over the square root of 18. Now, if I were a glutton for punishment, I'd multiply top and bottom by radical 18, which would give me 2 radical 18 over 18. And you see here, I would still simplify. That would give me 2 times the square root of 18 is 9 times 2 over 18. So that would give me 2 times 3 radical 2 over 18, which would give me 6 radical 2 over 18. And the 6 over 18 I could reduce to 1/3. Wow, that was a mouthful, wasn't it? However, instead, with that 2 over radical 18, If you can recognize it, if I take that 18 and multiply it by 2, that gives me 2 radical 2 over radical 36. And you see how it gives me smaller numbers to work with? And it eventually takes me to the same place. Both end up in the same place.
What if you simplified radical 18 at the beginning and then multiplied out the smaller number on the smaller radicand? Like,
Sure, you could do that. If I had 2 over the square root of 18, you could change that into 2 over the square root of 9 times 2, which would give me 2 over 3 radical 2. And then you can multiply top and bottom by radical 2. Most people don't do that first, though, because it's, it just seems easier to find the smaller number to multiply by. But it'll take us to exactly the same place. 2 radical 2 over 3 times 2 would give me 2 radical 2 over 6, or radical 2 over 3. It would work. It would take you to the same place. Next batch that we're doing are a lot more complicated. And I'm looking at my watch, and according to my watch, we've only got about 2 minutes left. So I'm going to stop here. If you're looking in that homework for P3, we have not gotten to ones that have addition or subtraction on with radicals in the denominator. Do not stress over those because we've run out of time. What I'm going to do is, whoops, I didn't want to stop the share yet. What I'm going to do is I'm going to, that homework P3, instead of being due on Wednesday the 16th, I'll push it back to Friday the 18th because we've only covered about half of it. All right?
Yep.
Isn't the P4 with the polynomials one due on the same day too?
That'll probably end up getting moved back also, but we'll wait and see how much we get through on Wednesday before we do that. All right?
All right, thank you.
Okay.
Can we get more time on quizzes?
Say that again?
For like the last quiz, I just thought it was a little bit short of time. Like I felt like I was rushing a little bit. I was just wondering if we can get more time on the next one.
Facts.
I didn't have enough time either.
Okay, I guess I'm surprised because I tried to give as much time as I usually give with in-class quizzes. I will try to make the time a little bit longer. I don't want to make them so that you have all of the time in the world, though, because, it just, that's just not feasible, and it just gives people, the first time when we went fully online in the spring, I decided that I would not put a time limit on tests. I'd leave them open all day for people because I didn't know what time people had to work on them. And there were some people who worked for 12 hours on a test. That's not right. I can't give you an infinite amount of time. At some point in time, you need to get some of this stuff done in a somewhat timely manner. I will try to be a little bit more liberal with the time on the next quiz, but if we were giving these in class at a certain point in time, I'd tell people, okay, all right, you just got to turn your paper in. So, okay? Which I don't think is what you wanted to hear, but that's my story and I'm sticking to it. So.
Have a good one.